Greetings, Electrochemistry students. This is Mr. Harper, and this is the first lecture out of Chapter 18, which is all about electrochemistry. And in this podcast, what we're going to do is we're going to review how to balance oxidation-reduction reactions and why this is important to us and how to predict whether or not they're going to be spontaneous. I'm also going to tell you guys a little other bits of trivia about how to use tables of standard reduction potentials and the information that tells you, and we're going to lead into the next topic, which is galvanic cells. And so hopefully what we're doing today is going to be familiar to you, but it does bear going over a little bit and is the perfect thing for you guys to do over spring break. So in this chapter, here's the big deal, that the stuff we're going to be talking about. So today we're going to cover balancing redox reactions. This course is through the podcast. After that, the next big topic is going to be galvanic cells. So we're going to talk about standard cells as well as the connection between voltage and equilibrium and how the voltage of a galvanic cell changes as the system approaches equilibrium. And then we're going to, or rather, you're probably going to read about batteries and fuel cells so you guys understand the difference in how they operate, but they both are the same idea. They both produce a voltage. Then after that, we're going to talk about electrolysis. And the difference between a galvanic cell and an electrolytic cell is that in a galvanic cell, as you guys are going to see, the oxidation-reduction reaction that takes place is spontaneous, whereas in an electrolytic cell, you have to force it to happen by applying a voltage because it is non-spontaneous. Okay? And we're going to talk about electrolysis of pure liquids and aqueous solutions and how that's different, and applications industrially of those things. And then, commercial applications, that sort of thing. Some of this you guys are going to have to read about in the book. Some of it we're going to cover in detail in class. But the challenge, as you guys are going to see, is going to be that once we get back from spring break, are going to have 2 weeks until the AP exam. And so we have the 1 week directly after spring break in which we're going to cover these topics about galvanic cells and electrolytic cells and all these things. And so there's going to be a lot of material to cover every day. And so I realize this is going to be a lot of work, and it is important that you are fully engaged and going strong to the finish because, believe it or not, guys, we are almost there to the AP exam. And so the title of this chapter is Electrochemistry, and that's what this is all about. And your book says it very well. What this is really all about, electrochemistry, is the study of the interchange of chemical and electrical energy. We're going to tie this in when we're talking about cell potential and voltage and all these things. Really, this is all because of changes in free energy and differences in potential energy of electrons when they're in one point and another. And so just keep in mind that what we're talking about here is really conversions of stored chemical potential energy into usable electrical energy. Okay? But more on that later on. Today what we're talking about is balancing equations. Okay? And as you guys are going to see, we're going to deal with spontaneous and non-spontaneous processes, and we'll talk more about that. There was something I was going to say with that, and I completely forget what it was. Okay. So, before you guys left for break, I should have given you a handout that you guys have already got that details how to balance a redox reaction and the steps involved in balancing a redox reaction. And we've already done this. If you guys remember way back last semester, we did this lab, which was really, I think, one of the best things actually we did all year. It was pretty fantastic, where you guys titrated not sodium hydroxide, you titrated hydrogen peroxide from the store using potassium permanganate solution. That was an oxidation reduction titration. And if you guys recall, I showed you guys how to balance redox reactions prior to that. If you still have the materials from that era, that is good, because that's going to help you right now, and hopefully you guys remember. But in case you don't, here's a refresher. If we're going to balance a redox reaction that is occurring in acidic or basic condition, there's a series of steps that we're going to follow. And the book phrases it in a slightly different fashion. You should go through and read this part of your textbook, but I think it condenses a couple of these steps down into fewer, but it's the same basic idea. So the first thing we're going to do is we're going to start by writing the unbalanced equation for the reaction. It is possible in the AP exam that it might give you a verbal equation, like in words, in which case you'll have to translate the names of the chemicals into their formula. Okay? We're going to identify what's getting oxidized, what's getting reduced, and then figure out what the products are that it makes. And then we go about balancing the different elements. So first we balance things besides hydrogen and oxygen. Then we balance oxygen and then hydrogen by doing different things. and then we balance charge by adding electrons to the appropriate side of the equation, and then you have to multiply so that you produce the same amount of electrons in the oxidation step as you consume in the reduction step, and then we add the two equations together and cancel duplicates, and then whatever. And then the only difference is that if we're doing this in basic solution, there's a last step there where we're going to convert H plus ions into water by adding hydroxide to both sides of the equation. Okay? If you guys don't remember all these steps, that's fine. You will probably again after doing a few problems. I'm going to do a couple examples here with you guys to illustrate how this works, and then I'm going to show you guys why this is important, okay? And why it's going to matter in this unit. Okay, not just why it's important, but why it's going to matter to you in this unit, okay? So we're going to start with something very simple. We're going to take a look here at this reaction, where we have a cerium 4 plus ion and a tin 2 plus ion becoming cerium 3 plus and tin 4 plus. Now, if you guys look here at this equation, this is very simple because it doesn't specify in the equation that this is occurring in acidic, basic, or neutral solution. We don't see any H+, we don't see any hydroxide, and so we can assume that this reaction between these ions is just happening in pure water, okay? Now, we have the unbalanced equation right here. The next thing we want to do here is kind of separate this out into oxidation and reduction steps, okay? First, a little bit of vocabulary. What does it mean to be oxidized? Well, if something gets oxidized, that means that the charge is increasing because it is losing electrons. If you guys look here at the the unbalanced equation, rather, you guys can see that the thing that's being oxidized is tin. Tin starts at 2 plus ion, it's becoming tin 4 plus. Okay? So that guy is getting oxidized, which means that it is losing electrons. So I can write the oxidation half reaction like this. Okay, so we have tin 2 plus is going to be changed into tin 4 plus. Okay? And then the thing that is getting reduced, the thing gaining electrons, is going to be our cerium ion. So cerium starts as a 4 plus, it's getting reduced to a 3 plus ion, so that means it must be gaining electrons. So cerium 4 plus is going to go down to cerium 3 plus. Okay? A little more vocabulary for you guys. You might remember that this thing here, the cerium, okay, which the thing that is getting reduced is called the oxidizing agent, because that is the thing that is taking electrons away from the other thing. So if you guys can imagine, this ion here is taking electrons away from the tin, and so that's causing tin to become oxidized. And so we call this guy the oxidizing agent. Tin in this reaction would be termed the reducing agent, and that is because this guy is the one giving up electrons to the cerium ion. Since it gives it electrons, it is causing this guy to be reduced and changed into the 3 plus ion. Okay? Now, just looking around here, because the only things we have in the equation are tin and cerium, we can skip a couple steps. We don't have to balance oxygen and hydrogen, and we can see that we have the same number of tin on both sides of this equation, same number of cerium on both sides of this equation right here as well. So now we can just go straight to adding electrons to balance the baby. Okay, now we always add electrons to the most positive side. If you look at the top reaction, you can see that the tin 4 plus is more positive. So we're going to add electrons to this side in order to make the charges on the product and reactant side the same. This is 4 plus, this is 2 plus. That tells me I got to add 2 electrons to the product side there. And that makes sense because in an oxidation step, something loses electrons. And in that part of the reaction, then that half reaction, the oxidation half reaction, electrons get produced. In the reduction half reaction, it's the opposite. You'll always see electrons on the reactant side. If we look, this is a 4 plus, that's a 3 plus. That tells me I have to add 1 electron to that side. So that the total charge over here is 3 plus, the total charge over there is 3 plus, and yeah. Okay? To get the total equation, I got to add those guys together, but before I can do that, I need to make sure that the same number of electrons are used here as get produced up here. Here 2 electrons are produced, here 1 electron is produced, so that tells me I have to multiply this bottom half reaction by 2. If I do that, I'm going to get tin 2 plus, because by the way, the electrons then will cancel, okay? Tin 2 plus 2 cerium 4 plus is going to yield tin 4 plus 2 cerium 3 plus. And there we go. Now that equation there is balanced. Okay, and if we look at, we've produced 2 electrons in the oxidation step, and then use 2 electrons in the reduction step, and so life is beautiful. That's easy. Excuse me. May it be on the AP test we have something so simple. Let's look at things that are slightly more complex. So we'll take a look first at one that is happening in acidic solution. Okay? So we're going to balance this equation here where we have permanganate and iron 2 plus, and getting changed iron 3 plus and Mn 2 plus. Okay? Now, if you guys take a look at the handouts I gave you guys before break, I gave you a table of common oxidizing agents. You don't have to memorize all those things. There's a couple that you guys have got to know. One of them is hydrogen peroxide. You should recognize that hydrogen peroxide is going to act as an oxidizing agent because that's pretty common. You should recognize that the dichromate ion, Cr2O7 2-, is a strong oxidizing agent. And any equation in which you see dichromate, that tells you that is going to oxidize something. And the other one you guys need to remember is probably the second most common, is permanganate. Permanganate ion is a strong oxidizing agent, and anytime you see that in an equation, that is going to act as an oxidizing agent, is going to take electrons away from something. So in this equation, you guys can see, if we take a look here, okay, iron is going from a 2 plus to a 3 plus. It is getting oxidized. If you look at the manganese in permanganate, its oxidation number is +7 over here, and over here it is +2, so manganese is getting reduced, okay? This is my unbalanced equation. Let's separate this into oxidation and reduction half reactions, okay? And again, just to review, the permanganate, this guy here is my oxidizing agent, okay? And then the iron 2 plus ion, that guy is the reducing agent, okay? This guy gets oxidized. So in the oxidation half reaction, I'm going to write this down. Iron 2 plus goes to iron 3 plus. In my reduction step, we're going to have permanganate, MnO4 minus, is going to go to Mn2 plus. Okay, now we got to go about balancing everything. Okay, if I look at the top, iron's balanced, and I don't have any atoms besides iron. If I look at the bottom, manganese is the same on both sides, but I have these oxygens I have to account for. To balance the oxygens, I must add water to the oxygen deficient side. That'd be the products. So I'm going to add over here 4 water, and the reason why 4 water is because I got to have 4 oxygens, and there we go. Now, of course, you guys will notice that this causes the hydrogens to be out of balance. On this side, I added 8 hydrogens, so I have to add 8 hydrogens over here. And I'm going to do that in the form of H plus ions. So I'm going to add 8 H plus to that side to balance the hydrogens. Finally, I've got to balance the charge in this half reaction. Over here, the total charge is +7. Over here, it's +2. To make those equal, I've got to add 5 electrons to that side, and yeah, okay. This equation is now balanced for that half reaction. For the oxidation half reaction, all we got to do is balance charge. You can see we're going to do that here by adding 1 electron to the product side, okay? Both my half reactions are now balanced. It's time to add those together. First, I got to multiply the top equation by 5. And I do that because we produce a single electron. Over here, 5 electrons get used, and those amounts have to be equal. So if I multiply, the electrons are going to cancel out. We don't show them as part of the overall equation. And so the total equation will be 5 Fe2 plus permanganate, MnO4 minus, okay, plus 8H plus yields 5 Fe3 plus Mn2 plus 4 water, and there we go, yeehaw. Okay, that would be the total overall balanced oxidation reduction reaction. In this reaction, what of course is happening is that the iron is transferring electrons here to permanganate. Permanganate is taking them away, and the manganese in permanganate gets reduced to manganese 2 plus. So keep that in mind, guys. And all these reactions that we're looking at, these oxidation reduction reactions, these are really talking about a transfer of electrons. Okay. We're going to do another one here. Now, actually, what I would like you guys to do is to pause the podcast and do this on your own first, and then come back and see my explanation. So go ahead and pause. Okay, and we're back. Ladies and gentlemen, if you guys take a look at this equation, right here, okay? So we're going to separate this into oxidation reduction half reactions, okay? Now, remember I told you guys a second ago that anytime you see dichromate, that screams to you that it is an oxidizing agent, and in fact that is true here. This is an oxidizing agent, so that is going to get reduced in the reduction half reaction. So this is going to be Cr2O7 2 minus, gets reduced to something. Over here on the product side, you can see we got chromium over there, so this is going to get reduced over here to Cr3+, okay? In the oxidation step, okay, the thing that you guys can see is getting oxidized clearly is, in this case, the ethanol. You could go through and calculate oxidation numbers of all these guys over here, but you can see that over here, the carbon has a higher oxidation state of +4, okay, and the carbon dioxide, and so that is getting oxidized, okay? If I take this guy here, so that my ethanol, C2H5OH, and I turn it into carbon dioxide here as a product, okay, that's the one thing really that I can write down at this stage, okay, for that right there. Now you're going to see here that in this equation, okay, we have water as a product, we have H plus over here as a reactant. Well, that's going to come out as part of these half reactions as I go through and balance them. Let's do the top one first. Okay, so I've got these half reactions. First thing I'm going to do is balance atoms besides hydrogen and oxygen. So to do that, I'm going to slap a 2 here. So I got 2 carbons over here and 2 carbons over here. Okay, if I now look at the second thing is going to be oxygen. Over here, I've got a total of 4. Over here, I've just got the 1. So I'm going to add 3 waters over here. Okay, and so now oxygen is the same on both sides. I got 4 here and I got 4 there. And then now if I go through and I balance hydrogens, you guys can see that over here I've got a total of 6, and then plus 6 more is 12. Holy mackerel, 12 hydrogens. And so that means I got to add 12 H plus ions over here to this side of the equation. Okay, once I've added the 12H plus to that side, you guys can see the charge now is not balanced, so I've got to add electrons to this side to make the charge equal. I'm going to add 12 electrons to that side to make the charges the same, because over here now the total charge is 0, over here now the total charge is 0, and that half reaction is balanced. Okay? If we look at the bottom one, I've got Cr2O7 goes to chromium. Well, chromium is unbalanced, so I got to put a 2 there in order to make that balance. Okay, and then if I look over here, I've got 7 oxygens, which means I've got to have 7 oxygens over here. I do that by adding 7 waters. Okay, and then to balance the hydrogens on this side, I'm going to add plus, in this case, I've got 14 hydrogens here, and so I'm going to add 14 H plus, L and mackerel H plus ions to that side. If I look now, the charge is not balanced. Over here, the total charge is plus 6, because I've got 2 of those. Over here, the total charge is plus 12, and so I've got to add 6 electrons to that side of the equation so that the charges will balance. Okay? If I look now, I've got to make sure, before I add the 2 half reactions together, I need to make sure that I'm using the same electrons here as I produce up there, and so I got to multiply the bottom equation by 2. If I do that, I'll have 12 electrons and 12 electrons, so those cancel out and are not shown in the overall equation. The total equation would be ethanol, C2H5OH, plus 3H2O, is plus 2 dichromate, Cr2O7 2 minus, plus 2 times 14 is 28, H plus, yields as products, 2CO2 plus 12H plus from the top equation, and then plus 4 Cr3 plus 7 H2O. Now, sorry, it's kind of sloppy there. Okay, now this equation can't be simplified because you can see we've got some duplicates. I got 12H plus on this side, and I got 28 over here, so those are going to cancel. And I go down to 16 on that side. On this side, I've got 7 water. On this side, I got 3, so those are going to go away, and this goes down to 4. So if I look at the total, overall, after removing duplicates, we have ethanol, C2H5OH, okay, plus 2 Cr2O7 2 minus, plus 16H plus, yields 2 carbon dioxide, plus 4 Cr3 plus 4 H2O, and there we go. Now that equation is balance. Now, a little bit of trivia for you guys. It used to be, before the advent and the popularity of all these electrode-controlled ones, that breathalyzers used to use exactly this same reaction right here to detect alcohol in somebody's breath. It used to be that the breathalyzer cartridge contained a sample of potassium dichromate. The dichromate ion is orange. When this gets reduced, when the chromium gets reduced, chromium 3 plus is kind of a blue-green color, and so the cartridge would change based on how much ethanol was on the guy's breath and to what degree this was changed into chromium 3 plus. I really want to operate the breathalyzer at prom. That would be awesome. Hopefully they'll let me do that. It doesn't use dichromate anymore, unfortunately, but it's still cool. Okay. Let's do one in a basic solution, guys. Okay, now again, if you find this painfully simple, you don't necessarily have to wade through these examples. Okay, but here's one where we got this, and we're using this one out of your book because I think this is a good example right here. Okay, so here we go. So we have the reaction here of silver with cyanide to make and oxygen to make that silver cyanide complex ion right there. Okay, so the trick with this reaction right here is you might take a look at this and say, okay, well here silver is a 0, and here silver is a plus, and here cyanide, the whole thing's a -1 ion, but over here it's a -1 ion. And so I can see silver getting oxidized, but what's getting reduced? Well, you see this reaction here happens in the presence of oxygen, right? And so if we separate these things out into my oxidation and reduction half reactions, right? Well, in the oxidation half reaction, we just saw that silver is going to go to this complex ion over here, silver cyanide, but in the process, its oxidation number increases. Well, the reduction half reaction has got to then involve this guy getting reduced to something. But you see, there aren't any other products. That's because the equation isn't balanced yet, right? So the reduction step, this oxygen is going to get, which by the way is the oxidizing agent in the reaction, okay, this is going to get reduced, okay, to something. Now, on the other side, I don't have any oxygen, and so I got to balance that by adding water. I'm going to add 2 water on the other side here, and then to balance the hydrogens, I'm going to add H plus to this side, you're going to see, and then now to balance charge, I'm going to add 4 electrons. So that is the reduction half reaction for oxygen. Up here at the top, oh yeah, I forgot to show the cyanide ions over here. Okay, up here at the top, this half reaction, of course, is not done, because if we look at the charge over here, so, you know, if I look at the atoms, right, we have the same number of silver, the same carbon, the same nitrogens, but my charge is not the same on both sides. On the product side, it's just -1. Over here, it's -2, since I have 2 cyanides. That tells me that to this side over here, I've got to add an electron so that the charges are going to balance. Okay. Before I add these 2 half reactions together, I got to make sure electrons equalize. Down here on the bottom, 4 electrons get used in that half reaction. 1 is produced up here, so I got to multiply that baby by 4. And so when I do that, what I'm going to get is 4 silver react with 8 cyanide, Cn minus, okay, and then they're going to react with an oxygen, and then 4 H plus, and this is going to yield on the top 4 of these complex ions, silver cyanide thingy, okay, and then on the bottom we have the 2 waters, so plus 2 H2O, okay. Now, here's the trick, is that I'm telling you guys this is going to be a reaction in basic solution, but right now we're showing H plus ions, so it's not set up like a basic solution. To turn this into a basic solution now, I'm going to add hydroxide to both sides to convert my H plus to water. Since I got 4 H plus, that means I'm going to add 4 hydroxide to this side, and what I got to do on this side, I got to do over here too, so we're going to add plus 4 hydroxide over here. These become now 4 water, okay, and these are gone, okay, and if you look, since these become 4 water, over here I've got 2 water, so that's going to cancel, and this goes down to 2. So now if I write down the overall total balanced thingy, we're going to have 4 silver plus 8 cyanide plus O2 plus 2 H2O yields 4 silver cyanide things plus 4 OH minus. And life is beautiful, ladies and gentlemen. Okay? This is the total balance equation for that reaction. Okay? Alright. Now, that's how you balance a redox reaction. The next thing I'm going to show you guys here in this podcast is how to determine if, in fact, one is going to happen. Because not every possible, conceivable redox reaction is actually going to occur. In order to tell if a redox reaction occurs, well, only ones that are spontaneous are actually going to occur. So the ones that have a negative delta G value, which we'll look at later on, okay, are going to be the ones that actually occur. Now, with redox reactions, we're not going to go through and look at my free energy of formation values and try to calculate it or anything like that. We're going to do this a different way. What you guys are going to look at is something called the cell potential. Okay? So a redox reaction, an oxidation-reduction reaction, is going to occur spontaneously if the overall cell potential for the process is positive. Okay? Now, cell potential is symbolized sometimes, if you're lazy, by an uppercase E, but that's not good because that also means energy. It is correctly symbolized by a Greek letter epsilon. I show you guys this because I don't want you to be tripped up, and just in case the College Board gets lazy on the test. Okay? Now, each half reaction, and by the way, guys, there are tables and tables and tables of different half reactions. There's one in your book, let me see what page it's on, that we're going to reference here in just a second. It's on page 845, okay, which is a table of a whole bunch of different half reactions and their associated, okay, I can't write them right for some reason. There we go, kind of, page 845, okay. It's got a whole bunch of different half reactions, then the potentials are measured and tabulated there. I also gave you guys one that has been used on the AP test previously that shows a whole bunch of different half reactions and their associated potential. You'll want to keep track of that. Now, potential here means, okay, so this is kind of an elusive term. Potential is kind of short for potential difference, okay? And what this has to do is the potential energy of the electron when it is in different positions, basically, okay? But the cell potential, in any case, we don't have to worry about the theory of it so much right now, but what this is going to tell you for a half reaction is how favorable that is, okay? So each half reaction has a potential, and the potential measures whether or not that is a favorable half reaction, okay? The overall redox reaction has a potential called the cell potential. And I get that by adding together the half reactions, each half reaction, and their associated potential. I'm going to show you guys an example of that here really quick, okay, in just a second, and you'll see the importance and whatever of that, okay? Now, in your book, and on the AP exam, the periodic table, and on the sheet they're going to give you, okay, these are going to be given as standard potentials, okay, and the symbol, of course, for standard is that guy right there, meaning that the potential was measured under standard conditions, okay. Now, when we were talking about free energy, right, the standard conditions were 298 Kelvin and 1 bar of pressure and so on and so forth. The same thing is true here, but I'm just highlighting that the concentrations are 1 molar of the ions in solution. That's going to be important because the concentrations of ions in solution can vary. If we're talking about a standard potential, that means the concentration is 1 molar, okay? And these are all measured relative to something called the hydrogen electrode, okay? So, to summarize, if this makes sense, okay, the potential, okay, for a half reaction measures how favorable that reaction is. And we have to have a point of reference in chemistry. If you guys have probably seen, like, when we're calculating, heat and all these sorts of things, right? We're always looking at a change in something, right? Because there is no like absolute reference for a potential. So we have to have a point that we say is the zero for the scale. And so there's a particular oxidation reduction reaction, which is what goes on at the hydrogen electrode that we define as being the 0 point. And so I'm going to show you guys that here really quick, okay? So this is what the hydrogen electrode looks like, and here's what happens in that reaction. So here we have a platinum electrode, which we'll talk about what an electrode is later, okay, immersed in an acidic solution where we have H plus ions at a concentration of 1 molar. There's this is a glass housing here around it, and there's an inlet where we have hydrogen gas going in at a pressure of 1 bar. At the surface of this electrode, here's what happens, is we take H plus ions, and these guys combine with electrons, and they are reduced to hydrogen gas. Or it can happen that the opposite reaction occurs, so that hydrogen gets oxidized to H plus and then 2 electrons, okay? These reactions right here are defined to have a potential, a standard potential, when the pressure is 1 bar and the concentration is 1 molar, of 0. And 0.00 volts. Volts is the unit that we measure potential in, all right? So every half reaction that you guys are going to look at is measured relative to this, by comparing it to this reaction. That'll make more sense as time goes on. Okay, so here's a table of some various half reactions, and this is taken out of your textbook. This is the one that I told you guys is on page 845. Okay, you guys can go look at it here at your leisure. And so if you take a look, okay, you'll see that each of these reactions is written as being a reduction half reaction. Okay, because they're all written as reduction half reactions, they're called reduction potentials here in the table. Now, of course, when I'm doing problems and doing math later on, any redox reaction must have an oxidation and reduction both half reaction, and so you can of course make this reaction, for example, an oxidation reaction by just flipping around, right? So say we look at this one right here, right? The reverse process would be Ag plus goes to Ag2 plus an electron, and so that would be the oxidation process. If I flip that around, just like we've done with previous things, then I would flip around the sign of the potential, and that guy would be negative or whatever, okay? So there we go, okay? Now, here's what the potentials tell you. Potential tells you how favorable a half reaction is. And this is kind of, people get this confused sometimes because remember for delta G we said that delta G has got to be negative for a spontaneous process? Well, for a favorable half reaction, the potential is going to be positive. And the more positive that potential is, the more favorable the half reaction. So you guys can see here the reduction of fluorine. Okay, that has a very high potential. It's the highest one on the table because that's a very favorable process. And as we go down the table, then that the favorability decreases, becomes less and 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 less. And then finally we get here to the reduction of H plus ions. This is what happens to the hydrogen electrode. This is 0. And then all these guys down here have got negative potentials. What these negative potentials mean is that these half reactions do not have a strong tendency to occur and are not favorable. And that makes sense, right? Because if you look here at lithium being reduced, for example, lithium ion plus an electron making lithium, okay, that has a potential of negative 3.05 volts. Well, you don't ever find lithium in nature, right, like this. It's never as lithium metal, it's always as lithium ions. Because this reaction, the reduction of lithium ions, is very unfavorable and does not really have a strong tendency to happen, okay? And there we have it. Now, here's something that's kind of interesting, right? If you think about this, in an oxidation-reduction reaction, the thing that gets reduced, that is going to accept electrons, is the oxidizing agent in the reaction, okay? So if you look at this table, of all the things here, fluorine is the strongest oxidizing agent, okay? And as we, go this way, up the table, my things here that I'm showing, the various chemicals involved, like, dichromate and lead oxide and whatever, become better and better and better and better oxidizing agents and are more likely to be reduced. Okay? If you look at these guys down here, these have a negative potential. Okay? But if you think about then the reverse process, like for example, if I take lithium and I flip that reaction around, so lithium goes to lithium plus an electron, that reaction right there has got a positive 3.05 volt potential. And so what this is telling me here is that, well, if it's shown this way, that reaction is unfavorable. Flipping it around is very favorable, okay? And so lithium metal is likely to be oxidized, whereas if you look over here, fluorine gas is likely to be reduced. This guy is going to act as an oxidizing agent. This guy in a redox reaction will act like a reducing agent. And ladies and gentlemen, life is beautiful, okay? Now here's how you guys are going to, one way you guys will use this, okay, is that one reason why this matters is we can use this idea of potentials for half reactions to predict whether or not a redox reaction is spontaneous. So let's consider one that we already looked at, which was the reaction between iron 2 plus and permanganate ions. Okay, we already saw here that my half reactions looked like this. We had the oxidation was iron 2 plus goes to iron 3 plus an electron. Okay. And for that half reaction right there, okay, I can look it up in a table. It's not in that one that was on page 845. But for this half reaction, this is actually going to have a potential right here of negative 0.77 volts. So looking at this in isolation, it might look like, well, that half reaction, it's not really all that favorable, right? Well, if I look at the other one here, which was the reduction half reaction, so permanganate gets reduced to manganese 2 plus, and then plus 4H2O, and then on this side we're going to have 8H plus, and then 5 electrons, and whatever. If I flip back here to my table we looked at just a second ago, that baby is right here. Okay, you guys can see that half reaction has a potential of 1.51 volts. Okay? If I add this together to get the total equation, or the total reaction like we had before, and I multiply this guy by 5, I'm going to get 5 Fe2 plus 8H plus permanganate MnO4 minus is going to yield 5 Fe3 plus Mn2 plus 4H2O. Okay? The overall potential for that half reaction is going to be the sum of these two right here. Now you're going to say, well, Mr. Harper, wait a second. If I multiply this half reaction by 5, don't I multiply the potential by 5? The answer to that is no. You don't multiply the cell potential. The reason being this is an intensive property and does not depend on the amount of this we have going on. Okay? So if I add these guys here together, if we just kind of like do this in our heads, right, the cell potential is positive 0.74 volts. And so we've just calculated that this overall reaction has a positive cell potential, a positive overall potential. And as you guys are going to see, a positive overall potential corresponds to a negative free energy change. And so this right here is going to be a spontaneous redox reaction. Okay? Now you're going to say, Mr. Harper, that's very interesting. I'm very glad that we can predict, using this methodology, whether or not a redox reaction is going to be spontaneous. But is there any other reason why this matters? And the answer to this is yes. Okay? Now, you guys have noticed here that the unit I'm using is volts for the potential. Okay? In this reaction, you guys can imagine, if I were to conduct it by pouring my reactants into a flask, right? So I put my iron solution and my permanganate solution in here together. These guys react. In this reaction, what happens is there is a transfer of electrons from the iron to the permanganate. Okay? Now, if I conduct the reaction by pouring these reactions together into a flask, to where they're in direct contact with each other, then the electrons are going to transfer directly, and you're going to see the redox reaction happen, but we can't really harness it to do anything useful. But then imagine, what if we were able to harness the electrons, because that's what's happening here, is electrons get transferred from one thing to another. What if we were able to make them do something useful? And so we could do that, maybe, by what if we separated these two reactants from each other, like my iron and my permanganates, and we had them in separate compartments. And say that then we allowed electrons to transfer between permanganate and iron, but we made it happen through a wire. And so my iron would lose electrons, and those electrons could go here and travel through the wire, and then get to my permanganates by doing that, going through that wire. And then imagine that we put something here in the circuit, like, for example, let's say, this is a terrible picture, but let's say that, for example, I had a light bulb that I wanted to power, and I put that guy in there, and so then as electrons went through the wire, carrying a certain amount of force, they went through my light bulb and caused it to illuminate, and whatever. Would that be useful? And yes, of course, that would. This is what we're talking about this week. This right here is the essence of a galvanic cell. Now, it's missing a few parts. As you guys are going to see, we've got to connect the beakers here with something called a salt bridge so that we can allow ions to move back and forth and equalize the charge and things of that nature. But that is why this is all very useful to understand, is that if I understand the redox reactions going on, this is essentially what batteries are. We have the two half reactions separated, and we force electrons to travel from one component to the other through a wire, and we harness them to do useful work. And for this reaction, if the reaction were occurring with a 1 molar concentration of this guy and a 1 molar concentration of that guy, so it's standard conditions, then the potential for that cell would be positive 0.74 volts, and that's the amount of voltage this would generate, which is about half of what a AA battery will generate. Ladies and gentlemen, I hope this has been useful. I hope you find this interesting. So with this information, go forth and do chemistry. Next, we'll talk about galvanic cells. That is for another day. Hope you guys are having a nice, great break. I will see you on Monday, the 21st. Hasta la vista.